Now that we know how to find chi-square critical values, we're going to use them to find confidence intervals for both population standard deviation and the population variance. Now take a moment and look at these different formulas because they're not as different as you think they are. They're exactly the same, actually. It's just that the standard deviation, because it isn't squared, you have to take the square root of the same results for your variance. So you have two boundaries for your variance, your lower bound, your upper bound. See how everything's squared in there? That's fine because it's variance and variance is squared. Well, if you want standard deviation, then you have to take the square root of that. That's why we always said that variance is actually easier to work with because variance is everything standard deviation is just squared, right? So you don't have to deal with the big honkin' square root in there. All right, so what are some requirements in order to construct an interval for sigma squared or sigma, either one? And there are only two big requirements. It has to be a simple random sample, like everything in this course. We don't work with biased samples. They're extremely difficult to work with. Quite frankly, for the most part, they should not be worked with at all. And you have to have your data come from a population that is normally distributed. Period. The end. You cannot have it be, oh, the sample's large enough. Remember how in chapter 8 and in section 9.1, let me scroll back to 9.1 for a sec. Here, in section 9.1, we said, okay, to ensure normal, we just have to have n times p times 1 minus p be greater than 10. That'll be good enough. And then in section 9.2, we said, oh, okay, n can be greater than 30. That'll be good enough. But there is no such provision in 9.3 here when we look at the chi-square distribution, right? It says it is normally distributed, period. That's it, right? There is no, oh, bigger than 30 or n times p times 1 minus p. That just has to be normally distributed. All right, then you need to know your chi-square critical values, which you can find from the table, right? There is no other way to find them unless you're on a computer. And because that chi-square distribution is not symmetric, right? Remember, it's right skewed. So since it's not symmetric, let me just remind you, this is a picture of what it looks like. It's skewed right. Of course, they vary from picture to picture because they're all different for their different degrees of freedom, but essentially they're skewed right. And since they're not symmetric, that means that you cannot construct a confidence interval by doing what we've done before. What we've done in section 9.1 and 9.2 is you take your point estimate, which is p hat plus or minus your error, or x bar plus or minus your error, right? So p hat and x bar were your point estimates, and you just add and subtract away a margin of error. That will not work here. That's why these formulas look different than the rest of them. And you're going to have to find two separate boundaries and two separate critical values because they don't operate the same way that the z or the t distribution would work. They operate off the chi-square distribution, which doesn't have that whole positive negative thing that the other two distributions are having. And of course, since the TI calculator does not compute the chi-square value, it actually can't do this confidence interval either. So this is one confidence interval you have to work by hand. Just a reminder, though, you do not have to memorize the formula for these. They're actually in your inferential statistics sheet right here. So the variance is the top one, and the standard deviation is the exact same thing, it's just the bottom one, right? But they're one and the same, and you'll notice that I don't have a calculator option for this, like I did one prop z int, that's the calculator, or t interval, that's the calculator. There is no such option here because it doesn't exist. You will have to do these by hand. But it's okay. They're actually not that hard, I promise. All right, so let's look at the graduate record examination, the GRE test. It's a test required for admission to many U.S. graduate schools. The Educational Testing Service, ETS, which produces the test, claims that students' scores on the verbal reasoning portion of the GRE have a mean of 469 and a standard deviation of 120. Suppose a random sample of 10 students took their test and their scores are below. All right, so here are the 10 students here. And what they're talking about is the verbal portion of a big test, sort of like the SATs, but it's for graduate students. So you don't take it unless you've got your bachelor's degree already and you're about to start graduate school. All right, the first thing we need to do is verify that this distribution is normally distributed. Why do we need to do that? Well, because in order to make a confidence interval for either variance or standard deviation, whatever we're going to do here, you have to know that the data is normal. And this graph shows that because all the points are within those two boundary lines. There, and I just typed that up right there. So in order to make a confidence interval for either sigma or sigma squared, whichever one, we must know it's normal. This graph shows us the data were normal because all the points are within those boundaries. No points are outside the boundaries. All right, then we want to find the sample standard deviation and the sample variance. Well, if you look really carefully, you can see that I kind of gave it to you here, but let's remind ourselves. If you want to find the sample standard deviation for a data set like this, you need to grab your calculator and type in that data in stat edit. All right, so I put those in. Sorry, I paused you for a second. So I went to stat, I went to edit, cleared out my old data, typed in the new data. There you have it. Then you run stat, calculate, one variable statistics. L1 is where our list is. Always leave frequency list blank unless you're doing a weighted mean or an expected value from chapter 6, 6.1 in fact. And then go to calculate and run it. And what we're interested in is actually the S right here, 105.139. So that would be our sample standard deviation. Except I had somebody typed in wrong there. It's 361, sorry, my fault. So let me run it again. Stat, calculate, one variable, L1, that's good. Enter. And there we have it, 105.446, right there. Okay, so now we're going to take that and put it right in here. So that would be our S value, our sample standard deviation. And then the variance would be that value squared, right? So remember, you can do that a couple ways, but what you really need to do is take 105.446 and square it. The other option would be to take the variables button, use number 5, which is statistics, and see number 3 right there, that's your SX. And you square it, and that'll keep all the decimal places. There you go, 11118.9. So they're a tiny bit off, but the bottom one's actually more accurate than the top one because the top one was made from a rounded number, whereas this actually kept all the decimal places for us. But either way, it rounds to the same thing. So I'm going to say S squared is approximately 11118.9. There we have it. All right, now we're going to construct a confidence interval for the population variance. We're going to need to show the formula and all that stuff. All right, so I know I'm going to need formula, substitution, and result. And I know that the formula works this way, right? It's going to have the n-1, the s squared, and the chi-square values. And the chi-square values are actually different from each other, so you got to be careful. They're not exactly the same thing. Well, the beginning part of it is not going to be so bad. We know what n is. N is just how many there are in the sample. I mean, heck, we could even count it, although it did come out of our calculations when we ran it here. You know, might be nice in case it was a longer data set. It tells you n right there, n equals 10. Okay, so now we know n equals 10, or you could just count them. You know, you've got eyes. So then we will have to put 10 in, and we already know what s squared is. So let me put 10 here and 10 here. Now s squared is what we actually just found. That's the 11118.9. Or if you like, you could think of it as 105.446 squared, right? And then another 105.446 squared. But that's what the 11118.9 was. So all we need to do is find our chi-square values and we'll be fine. Okay, but the chi-square values, we're going to need that table to do that. And in order to do that, we're going to need to figure out alpha and 1 alpha over 2 and 1 minus alpha over 2. We need to figure out all that stuff. So your C level was 0.95, right? So that means that your alpha is 0.05, right? The complement of that. I'm going to put that right there. All right, so then it says right in there, right in the chi-square, it tells you what it wants. It wants alpha over 2. So you just do alpha over 2. That would be 0.025. Okay. And then you need the other one, which is 1 minus alpha over 2, which would be 0.975. All right, so those two are going to be your columns. So when you go to the table, the chi-square table, those are the columns we're going to look at. You can move this over. All right, so all we need to know is the row we're going to look at, and we'll be fine. Well, remember your degrees of freedom is your row, which is n minus 1, so that's 10 minus 1, and that's 9. So that's the row we're going to need from the table. All right, so let's go grab that table and look at it. Remember, you don't really have any options. This is the only choice you've got. So we have our chi-square table. Put that line down the middle. Now the chi-square value on the right is going to be 0.025, and I need to go to the 9th row. So that would be 19.023. So that's alpha over 2,1. Then the 1 minus alpha over 2,1 is over here, and it's going to be 2.700 because it's 0.975, 9 degrees of freedom. So there are the two chi-square values right there. Let me put those in right here. Right, and you get those from the table. So I'll have to go in here. The 19, the larger one actually goes on the left because it's on the right side of the curve, but it's a larger number, which means you want it to be on the left in order to make this number smaller. Remember, the bigger your denominator, the smaller your overall number is. And if you forget and mess it up, it's not that big of a deal if you switch them when it's over, right? And this one's 2.700. Okay, so smaller number over here, bigger number over here. All right. And then that will give us an answer. We just need to find it. All right, so let me clear that out of here. So I need to take 9 times 11118. How many ones were in that? 4 ones. 8.9, right? And then I need to divide it by 19.023. And there we have it. Or if you like, you could say 9 times 105.446 squared, hit the squared button, then divide that by 19.023. That will also work. They're a tiny bit different from each other. The top one's actually more accurate, right? And then you do the same thing, 9 times 11118.9, and then you divide it by the other number, which was 2.700. Technically, you don't need the 0 zeros in there, but that's fine. And then if you did the other way, if you went 9 times 105.446, you squared it, and you divide it by 2.700, you get 37062.86. So just a tiny bit different from each other. Technically, the ones that use the 11118 is more accurate because that one, if you recall, we found with the taking the variable button and having standard deviation get automatically squared for us by the calculator. Okay, so either way, if I round it, it's roughly this. All right, so that's how to find the confidence interval for population variance. Now, what if they asked you to do the confidence interval for population standard deviation? Well, you've actually done most of the work because if you look at the formulas, they're the same. It's just that the standard deviation one, you take a square root of it. That's it, right? So variance is squared, so you take the square root of that interval in order to find your values. So I'm going to need the square root of each of these numbers. So let me go grab my calculator. So I'm going to need the square root of 5260.47942. And then I'm going to need the square root of, let's see, 37063. So that gets me 72.529 and 192.518 roughly. So I'm going to go type all that up. 1 second. There we have it. All right, so we want to take the square root of the interval below, or interval above, excuse me. And there you have it. There's your result right there. Now let's pause right here, and then I'll come back for the last parts of this example to interpret that interval and so on.